Okay, so let's get started. Sorry. Okay, so let's get started. Yeah, so the goal of this lecture is really not to introduce something new, right? But really look back and try to summarize what we have been learning in the last 13 lectures, right? To introduce some structure about what we learned, right? Because we are learning in a pretty linear order, right? Sometimes it's kind of helpful to look back and try to think about the previous concept after you know about concept we introduced later. And also try to define some scope and convey some expectation that we have, what we kind of expect you guys to actually master after this course, right? And we can go through some simple kind of example questions, right? So that we see in previous year's exam, right? To just get on the same page about our expectation in the exam, right? So that's the goal for this lecture. Right? We are going to have two of such lectures. One is today, another is at the end of the semester. Right? After we finish the next chunk of lectures, we will do another lecture doing this type of review. Okay, so where are we, right? If you look back and think about what we have been learning in the last 13 lectures, essentially we talk about two things. The first one, we talk about how to use a database as a user. So we talk about both the theoretical aspect and also the system aspect. From the theoretical aspect, we talk about the data model. That is, you have a whole bunch of data, you need to impose some model such that you can talk about it, such that you can manage it. And the data model that we have been focused on in this whole course is relational model. And then we talk about two different ways for you to query your data. So what do we mean by query your data, right? You have all your data stored in your data model. That is, you have all your data in your relational model, that every single piece of information is a relation. And the query is a function that takes as input a whole bunch of relations and output a new one, right, in relational model. So there are so many different ways you can construct a query. From a theoretical perspective, we talk about two ways for you to do that. One way is called relational algebra, right? You can actually have an algebra expression, right? So, and then the database will know, this is a piece of information the user wants. And then we also talk about a different way of doing that. It is via relational calculus. You do not write your query as an expression. Instead, you write your query as a logical formula. If you put these two side by side and think about what their difference is, relational algebra is something imperative in the sense that as a user, you are telling the database an expression that if the database follows step by step, it's going to get the information you want. You are actually telling the database how to get the information you want. And relational calculus is a little bit at a higher level. That is, it is declarative in the sense that you are not telling the database how to get the information, but instead you are giving a declarative definition of the result. And it is database's job to try to figure out a way to get that piece of information for you. So one of this is imperative and one of this is declarative. When we are using a database system, we want the user to actually write something at a declarative level. And then we talk about some practical aspect, right? So we talk about how to use SQL as a language to query a real world database. And we do some hands-on sessions, right, to make sure you cannot play with a real world database system. And then we talk about another thing, right? So after you know how to store information in your database and how to query it, we talk about how to use the database to build one application that you want to build. So here, not only you need to understand how to use the database, but you kind of need to understand how to design the schema of your database applications to reflect the application you want to build in real world. And doing that involves multiple steps. So at the early step is conceptual modeling. That is, you want to precisely describe what you have in this application. There are so many different ways to do it. In this course, we talk about one way to do it. It is something that we call entity relationship model. Essentially, you model all the data, all the information you have in this application by a whole bunch of entity sets and their relationships. We talk about one way for you to write it down, that is via entity relationship diagram. And the second step is logical modeling, right? That is a step that takes as input the conceptual model you have and translate that into your logical model. And in this course, when we talk about logical model, we talk about a relational model. You want to take as input an entity relationship diagram and output a relational model schema. And after you do that, you need to worry about a whole bunch of things. One thing is data integrity, right? You have constraints in your application. For example, in your entity relationship diagram, you have cardinality constraints, right? How can we implement that? You have different type constraints, right? So we talk about different ways for you to enforce data integrity, right? So a whole bunch of integrity constraints. And we also talk about the notion of functional dependency for you to reason about data redundancy in your design. And then we talk about different normal forms. Each one of them will actually enforce some property on your design with respect to data redundancy. If you look back, this is pretty much all we have been learning in the last 13 lectures. And if you put them all together, our goal is really make you a good database user, right? When you go find a job, right? When you are building a real world application, we want you to be able to model your application, do conceptual modeling, do logical modeling, try to reason about the pros and cons of different type of design, know how to enforce data integrity to make sure whatever you put in your database have certain property, do not break your application, right? And we also want to make sure you as a user knows how to use the database to actually implement that. So this is the goal for the first 13 lecture. So if you look back, right, so essentially there are kind of multiple questions that we have been looking at. The first question is so what is the right way to think about our data, right? So that is the data modeling part. The second question is how to manipulate data in practice, right? So that is when we talk about the SQL queries. And then how to precisely describe your application, right? That is the conceptual modeling part, and how to ensure data integrity and how to ensure better design in your applications, right? So that is when we talk about integrity constraint, functional dependency, and the normal forms. So this is the overall structure of the first half of this course, okay? So when we talk about exam, right? So the principle is of similar style as previous years. So there's many multiple choice questions. Essentially, if you look back, so this is kind of one example structure. Of course, it might change slightly, right, for this year. But essentially, this is the thing that we care about. Okay, we care about entity relationship model, we talk relational model, algebra, SQL, right? And SQL is really, really important. We talk about constraints, dependency, normal forms, right? And then in the second half of the course, we are going to talk about query processing, transactions, so on and so forth. So essentially, after the first half, you should be able to know how to answer the first, for example, 9 questions in the exam, right? And then in the second half of the lecture of the course, we are going to talk about the rest. So for the rest of this lecture, right, we are going to really walk through of the content that we have been covered so far, right? If you have any questions, right, so just interrupt me and ask your questions, right? So this lecture could be a little bit more interactive. I'm here to answer your question. And also we cannot define the scope and try to calibrate our expectation on the exam, okay? Okay, so let's go back to the big picture and then let's try to understand the data modeling part, right? So that is the first component. How do we think about data? So in this lecture, our data model is something that people call relational model, which is very simple. Intuitively, you want to think about your data as a table, right? So as a real table in real world, right? So a table has a name, has a whole bunch of columns or attributes. Why do we call them? So the property of the column is every single value in the same column should have the same type, okay? And then you have a whole bunch of rows, right? So each row is intuitively corresponding to one instance of relationships between different entities, okay? So there's a schema in the relational model, right? A database schema is a set of relations, right? And each relation has a name, has a set of attributes or field or columns, no matter however you want to call it. And each attribute has a name and has a domain. And domain is kind of the set of values that you can take in that attribute. For example, you can have integer domain, you have string domain, right? So logically, right, if you define a schema like this, you intuitively define like a header of a table, have the name, you have, for example, 5 attributes, right? You do not have the content in the schema, right? So, and then you have the instance of this relation, which if you think about relation as a table, instance is start to fill the content of that table. So for each relation R, assuming you define n different attributes, and each one of them has a domain, D1 to Dn, an instance of this relation is a set of tuples that can take value, and like each tuple can take value in the cross product of all these domains, D1 to Dn. So intuitively, right, the instance is like the content of the table. If you have a schema like this, this is one database instance, right? You have 3 students in this relation, you have student ID, name, login, so on and so forth. One thing that to really keep in mind is when we talk about relational model, we always assume relation is a set, right? That's very important. Well, we cannot have a duplicate in a relational model, okay? When we talk about theory, it's always a set. And second, the order of how you store this whole bunch of tuples doesn't matter in relational model in this course. Right? Of course, like people have been doing a whole bunch of extension of relational model to consider bag semantic, to consider different orders, right? But in this course, or also in the exam, when we talk about relational model, we always think about a set, okay? So as you will see in real world database system, when you are writing SQL queries, you are actually dealing with a bag, right? So like not a set semantic, right? So that's very important. So that's the assumption we are making in this course. When we talk about theory, it's always a set. When you talk about the practice, it is what it is in practice, that is the bag, okay? And we talk about more concepts in relational model, right? So inside the schema, you also have the notion of candidate key, right? So that's a minimal set of fields that identify each tuple uniquely. So we talk about this actually in the second lecture in the course, and we keep going back to it, right? Whenever we talk about integrity constraint, the notion of key comes in. Whenever we talk about functional dependency, right, in the last week, so the notion of candidate key comes in, right? So now I hope it's much more clear about what a key is, okay? So each relation contains a whole bunch of candidate key, and each candidate key is a minimal set of fields into minimal in the sense that if you remove any attribute from a candidate key, it cannot be a key anymore, okay? Candidate key is a minimal set of fields that identify each tuple in the relation uniquely, in the sense that if I know the value of this set of fields, I should be able to uniquely identify all the other values in all the other attributes, right? So in other sense, right? So if a set of attributes is a candidate key, it means that, right? So there's a functional dependency from that set of attributes to all the other attributes in relation R. Okay, so that's so many different ways to think about candidate key. Okay, so and you pick one of them to use as a primary key in relation R. Okay, that's relational model. And then each relation in relational model, okay, in theory, must have a key. Okay? And that's always possible because relational model has a set semantic. In the worst case, you can always take all the attributes which will form a key, right? So like if you cannot find the subset, right, taking all the attributes will give you that. So it's always possible for you to have a key for relation. So for example, right, so if you have kind of this data schema, right? You do underline, you say, okay, SID is a key, right? Essentially, you think about what that is doing is try to define all possible instances that is valid in your database, right? So, for example, if you define SID as a primary key, right? Essentially, what we are trying to do is tell database, okay, a relation look like the first one is okay, I can deal with that. But if you give me a relation look like second one, I'm going to give you an error because that's not what I want. Because in the second instance, right? So you have two tuples share the same student ID value, right? Which break the key constraint, right? So you can think about the key constraint as introducing some constraints about what is a valid instance, okay? Specifically, when you have the K as a key, right? Essentially, you are adding one condition for valid instance. That is, I cannot find the two tuples that share the value on the key, but have different value on the rest of attributes. Okay. So this is the definition of relational model, and this is one example of an instance, right, of relational database. You have a whole bunch of relations, right? So each relation has a name, has a set of attributes, has a key, right? And then one instance of the relation is a set of tuples. And now can query it, right? What is a query? A query is simply a function that takes as input a relational instance and output a new relation. Okay, so that's the definition of query in relational database. And the query language is defined by the set of functions you can express in that language. Okay, precisely that's what query language is. There are so many different ways you can query your data. So the first way is by using relational algebra, right? So that is an imperative way for you to query your data. So the intuition is very clear, right? Relation instance are set. So let's query it using set operations, right? So that's a very natural thing to do. So the basic operation you have in relational algebra, right? We talk about a whole bunch of those, like the union, the difference, right? So all of this you can do on site, right? Without any questions, right? You have selection, right? You have projection, you have cross product, you have renaming of the relation, and you have joins, right? We talk about all those operators and what they are doing. What's beautiful about relational algebra is that every single relation you have has the same type, has the same signature, in the sense that they take as input a list of relation and output a new one. Right? That means that you can actually put them together. For example, if you want to say, okay, give me all the customers who bought the iPhone, right? So you can actually have all those operators, like you can put them together, right? So it is possible to put them together because the output of each operator is still a relation, okay? So this gives you a relation algebra expression, right, that you can actually use as a query. However, this is an imperative way for you to query your data. And we also talk about another way to do it, and that is the declarative way. The high-level idea is really trying to tell the database not how to get your data, but try to define at a higher level the property I want in my result. So the high-level idea here is by using mathematical logic. That is, we think about each relation as a logical predicate, and then I can define the information I want using a logical formula. For example, right, so if you look at this query, essentially we are trying to say is that, okay, what is the result I want? My result will be a set of pairs. And the first thing in the pair is called PID, and second is CID. And I want everything returned to me in that set satisfy the following condition. That is, there exists an N and P such that PID N and P is in product, and there exists C and C such that CID, C and C is in customer, so on and so forth. As you can see, if you give this to a database, the database will actually not know how to run it, like a relational algebra expression. I cannot follow step by step to give you the answer. Database need to figure out, okay, so this is what the user wants. What is the corresponding relational algebra expression that can give the user what she wants? And the process of doing that is what database is going to do underneath the cover, and it's something we are going to talk about next week, about how database actually do that. So it is easy to see if you have this query, right? So you are going to get the same result as this relational algebra expressions. In fact, there is a kind of correspondence, one-to-one correspondence, and not one-to-one correspondence. And there's equivalency between a function you can write in relational algebra and a query you can specify in a subset of relational calculus. Okay. So in the exam, right? So how we are going to talk about it, right? So the skill we want you guys to have after this course, right? And our expectation is, if I give you a query that you want to ask, right? So you should be able to write down a relational algebra expression and a relational calculus expression. And second, given a relational algebra expression or relational calculus expression, you should be able to understand its semantics, right? So we really want you guys to understand a whole bunch of concepts, right? So that is, okay, relation is a set. That's very important, right, in this course. And also different operations, right, in relational algebra or relational calculus, right? What is union, what is intersection, right? What is semi-join, what is theta join, what is outer join, right? So, and how to read it and how to write it, right? So that is our expectation about what we really want you to know after this course. Right, so in the exam, right, so this is one type of question that we could ask, right? So this is from the previous exam, right? So for example, we could give you kind of a model, right? So here is the data you have airplane type, airport, so on and so forth, right? Each one of them, here is the whole bunch of attributes, here's the key, right? First, you should be able to understand it, right? By reading, you should be able to understand what we are talking about. Right? Now we might give you some queries to say, okay, so give me yeah, so like this is one query, right? So which flight perform on this day, right? So on and so forth, right? So, and then there's a whole bunch of corresponding possible ways to write it down, right? So a natural question to ask is actually, yeah, so like which of this relation algebra expression give you the result of each of these questions, right? So to really answer this question, you kind of need to understand pretty much how to read a relational algebra expression, right? So, and to do that, you need to understand all those operators and the underlying semantic of relational algebra expressions, okay? So that is what we really want you guys to know. So this is something similar, right? So we could give you some relation instances, right? And we give you some expressions, right? So when we ask, okay, so which one of these tuples is going to be in which relation, right? That's sorry, like which is going to be in which, like in the result of which kind of relation algebra expressions, right? So as long as you understand what each expression is trying to do, right? So this type of question should be trivial to it, okay? So this is about theory, right? So we talk about from the theoretical perspective, what do we mean by manipulating data? And then we switch gear to talk about the practical aspect. That is, in real world, when you have a database system or relational database system, how can you really do that, right? So the way to do it is by using a practical query language called SQL, right? So the structure of SQL is actually not that non-trivial, right? So think about if you are designing a language, right, for the user to write a relational calculus expression, right? So what would you have, right? So you need some way for them to define the schema of the table. You need some way for them to put information into the table, right? And you need some way for them to query it, right? So naturally, SQL have three kind of components. You have the data definition language for you to define the schema, right, and all the constraints. You have the data manipulation language for you to put information into a table and for you to update it. And you have the query language for you to take as input all the information you have in your database and output a new relation, right? So very natural. So the first paper describing SQL is actually published in 1974. right? And then you have a whole bunch of standards, right? So every couple of years to include in more and more functionalities that you can do in this language. So the first component of SQL, right, is the data definition language, right? So essentially it gives you a whole bunch of statements to define the schema of relation, right? So recall relation look like schema look like this in theory, right? In SQL, you need to give the name, give the set of attributes, give their type, right? So like most of the like programming languages, you have a whole bunch of predefined data type, right? So you can write a query look like this to actually create a table, a relation, whatever you want to call it, inside your database, right? So here, right, so when we first talk about it, right, so we haven't talked about the integrity constraint, right? But right now you should be able to read this without any problems, right? So I create a table, professor, I have 3 attributes, each one of them has a certain type, you have a default value for certain kind of attributes, and then you have some integrity constraint. Here I have a primary constraint for this attribute, personal number. What does it mean, right? In SQL, it means 2 things. First one, it need to be unique. Second, it cannot be null, right? We talk about this, right? So after we talk about it before Easter, right? Integrity constraints, right? So if you do this, database is going to create a relation for you, right? So, and then you can delete the relation, right? You can modify the structure, so on and so forth, right? Because we are talking about a query language, right? So, and the best way for to learn it is actually to try it, right? So that's why we have all those hands-on sessions for to get familiar with the real world kind of database systems, right? And of course, you can manipulate your data, right? You can insert information into your relation, right? You can delete information, you can update information, so on and so forth, right? There are so many different ways for you to populate a relation, right? You can do tuple by tuple, right? That could be very slow, right? For a whole bunch of reasons, right? You can actually load kind of a large CSV file or TSV file into your database in a batch, right? So all of this, right? So it's just some example about how to use kind of database systems, right? Very natural. We talk about the query language, right? So there's actually a very beautiful connection between all those theoretical query languages and the thing you are writing in practice. So most important, one of the most important query you are going to write is select from where, right? And that doesn't come from nowhere, right? So that's actually give you a way to express this type of relation algebra or relation calculus expressions that only have a selection, projection, and join, right? So there's the correspondence very clear, right? So whatever you want to select, you put that after from, right? Whatever you want to do projection on, you put that after select, and you put all the conditions, right, after where. So, and then, right, so there's a whole bunch of syntax triggers, and you can actually use it to join kind of multiple relations, right? So in general, right, so if you are trying to write a relational algebra expression look like this, you have, so like this one corresponding to this expression, right? So everything after from form a cross product, everything after where give you a selection condition, everything after select give you both the renaming of the attributes, the new name of attributes, and also the column you want to project on, right? So this is just one simple example about select from where, right? Which is probably the most popular construction you are going to use inside real-world database systems, and then and also its connection to the theoretical aspect that we talk about. And of course, right, when we talk about SQL, there's so much more, right? We spend kind of like 2 or 3 weeks talk about this, right? So again, the best way to do it is just go through all the queries that we have been talking about in the hands-on session, and go through the SQL query you are going to see in your book, right? And then try to understand them. It's not that hard, but you just need to practice. Okay? So whenever you like we know how to write a query, right? Just think about what you are achieving, right? You have a database system, you have a user, yeah, you are a user, right? So you have your memory, you have your hard drive. Whenever you create a table, a database is going to actually create a table that's going to be stored on your hard drive, such that if you pull the plug of your machine, when you restart it, the data will still be there, right? And then whenever you give a query, the database is going to bring the information all the way from hard drive to your memory to your database system, which is a very complex process that we are going to talk about next week, right? The goal of the database system is for you as a user, you do not understand the things on the left-hand side, okay? So it is database job to handle that for you. And you as a user only worry about kind of the logical part, which is on the right-hand side. So in the exam, right, so that is actually a key part of this course. Like one thing you want to make sure is after this course, you should be able to write a SQL query, given a description of the query in natural language, right? You should be able to know how to interact with the database. That's very important, right? And also if someone else give you a SQL query, right? So you should be able to understand what they're trying to do and what you are expecting in its result, right? So this is the two skill we really want you to have after this course. So I mean, to do that, right, there's a whole bunch of concepts, right? So we actually expect you to understand all the concepts that are necessary to understand all SQL queries in hands-on lecture, all queries in the exercise session, all queries in period exam, and all queries you are going to see in, I think, chapter 6 of the textbook. Okay, I know it's a lot, right? But this is really important components of this course. Okay? So we kind of expect you to understand what all those queries are doing. Okay, and also we expect you to understand a whole bunch of corner cases, right, to make sure you know that in practice. Don't get surprised, don't make a mistake in practice, right? So especially how different operators behave when the null value is involved. Okay, especially when you have average, when you have sum over null, right? What to expect in the result. That's also something we really want you to know. Okay. So in the exam, right, the questions are very natural once you master all those concepts, right? So for example, we could give you like, so this is how we created my database schema. Here's the information I have inside this relation, right? So we could ask you some questions, for example, so here's one SQL query, I select age from professor, union select age from professor, right? How many typos are you really expecting, right? So to do this type of thing, if you know what the query is doing, this is very, very easy, right? So what is it trying to do? You look at the professor table. Okay, you are selecting all the age from professor, right? So here you have this, you have a whole bunch of null values, you have 3 distinct values. When you do the union, right? So it has a set semantic. We will do union all as a back semantic. We talk about it, right? When you do union, it's a set semantic, right? And you we're going to do a selection, right? How many examples are going to have, right? So, since you have union, right? So you have like 4 examples, like 4 tuples in your result, right? So the best way to do it is have like go through previous exams, right? Open a real database system and run the query by yourself, right? And try to understand whether the result is consistent with your expectation. If it's not consistent with your expectation, think about it. If you still have question, send me an email or post a question on Moodle. We are here to help you. But you need to give us your question. Okay. So best way to get the question, right, is put this in a real database system, PostgreSQL, right? You run the query one by one, and to see whether you get surprised. Okay. We really rely on you to do that exercise by yourself, because otherwise I don't know how to teach you a programming language without you take the driver's seat to actually practice it. Okay. So the whole bunch of similar questions, right? For example, so here's one query, and you can see what we are trying to do, right? So we want you to understand what is ordered by, right? When there's no value in aggregation, what is the behavior, right? So here, count x, right? Only consider non-null values when x is not star, right? So that is the corner case we really want you guys to know, right? So how different scenarios for operator over null, right? So be really careful, right? But run this by yourself. If you get surprised and if you don't know why, let us know. That's very, very important. So this is about essentially how to use a database system, right? And after that, we talk about how to use a database to build an application, right? So the first step in the process is conceptual modeling. You want to build a real world applications, right? So the first step is try to capture the domain you want to be represented, right? So intuitively, right, if you want to build this tool example, right? So you in your mind can write down your requirement in English, right? So what are the data I want in the application? I want to have a product. A product has a name. Right? A product has a whole bunch of parts. Each part has a name, so on and so forth. But this is English, right? This is not something machine can understand, right? So the very first step, the conceptually modeling part, is try to write it down in such a precise way that everyone can understand, and also your machine can understand. Okay. One way to do it is by using an entity relationship diagram that looks like this, right? And the second step is really try to translate that into a logical model, which is your relational schema, right? And the third step is actually try to implement that for real, right? So let's talk about the conceptual modeling part. So here we talk about the entity relationship model, right? Where you have a whole bunch of entities in your application, right? You kind of specify them as a whole bunch of entity sets, right? So each entity set has a whole bunch of attributes, right? You draw it like this. If you want to have a person entity set in your application, meaning that, okay, in my application, I have a whole bunch of people, right? You can have one entity set called person, national ID, passport number, name, so on and so forth, right? So, and you could have relationships between all those entity sets, right? If you have two entity sets, you draw something like a diamond shape, right, in between, right? That's a relationship. For example, if you have person, if you have lecture, right? Person teach lecture, you can have one relationship here, right? Person takes lecture, you can have another relationship here, right? It's very simple. And each entity set has a key, right? So like whenever you have a unique identifier, right? You just draw underline, right? Here, right? To really say, okay, so like this attribute is a candidate key, so it's a primary key, right? And then we talk about a whole bunch of other concepts that's very important. We talk about what is role, right? What is kind of motivated relationships, right? So we talk about cardinality constraints, weak entities, generalization, right? We talk about a whole bunch of design principles, right? So all of this kind of very important, okay? We kind of expect you to know all of this. And the second step is logical modeling, right? You take as input the conceptual model, that's an ER diagram, and translate that into a rational model. And we talk about a whole bunch of principles, right, for you to do this, right? So one entity set in your entity relationship diagram will become one relation in your logical model, right? Each relationship will also become one relation in your relational model, right? And after do the translation, if you have multiple relations with the same key, right? So you might want to merge them, right? So, and then to be really careful about generalization, about weak entities, and how to do such translation. We talk about this in the lecture. So one thing to really keep in mind is there's one very tricky thing, which is cardinality, right? So there's many to one, one to many, right? All those cardinality constraints. When we do the translation, that could become very tricky, right? So assuming you have one entity relationship diagram look like this, right? You have three entity sites, your department, your location, you have employees, right? So you have this kinetic constraint, which means that, let's read that together, right? If you know the employee and locations, you can uniquely identify departments, right? So this is roughly what it's trying to say. And starting 2 weeks ago, right? So we know how to precisely say it, right? So this kinetic constraint means that there's a functional dependency, right? From employees' locations to department, right? Which means that department functionally dependent on the combination of employees and locations. Okay, so this kinetic constraint will introduce that functional dependency. Okay, and when you read about normal form, right? So that functional dependency will be there for you to understand whether a certain design is in certain normal form or not. Okay, so that's a connection. You have constraints in your ER diagram. That's a way for you to specify functional dependencies in your application. And once you know those, you can reason about the properties of your relational design. That's how everything fits together, okay? So when you have cardinality, when you design the kind of relation schema, right? Some of the design could be problematic, right? For example, we talk about this kind of example, it's not really something we want, right? Because the combination of this, right? So the three attributes, right? So it's not really a key, right? You cannot just put key there, right? Because of the kinetic constraint, right? So here, like a subset of it is a key, right? How to understand which attribute is a key, right? Here you have the functional dependency specified by your kinetic constraint, right? You can see, there's actually a functional dependency from address and SSN to all the other attributes, right? So, and also it's minimum in the sense that if I remove any of these attributes, it's not a key anymore, that functional dependency doesn't exist anymore, right? So, and then therefore this pair is a key. Okay, so that's how everything fit together. When we talk about ER diagram, right, we haven't talked about functional dependency yet, right? So now we talk about all the concept, right? So it's time to look back and try to put everything together, okay? So yeah, it can be tricky, right? So whenever you have a diagram look like this, right? So you could have one relation storing, like for example, the works in relationship. You have one relation stored the employees relation, right? So like employee entity set, right? So you could merge them together, right? So here, right, merge them together can have pros and cons, right? And last week we talked about normal forms, right? You can actually think about given this functional dependency, right? Which is there's a FD from employee to department, right? That is specified by your kinetic constraint, right? So these two designs, they are in different normal forms, right? And they could be in different normal forms, right? So, and then you can actually reason about the property of each of these designs. So for example, this is a pretty bad design, right? So assuming you have works in, you have department, if you decide to merge them, right? And you can think about, which normal form this like this design is in, right? And then you can actually think about whether that design has the property you want in your application, right? So in this case, clearly it's in a very low level of normal forms, right? So I don't even know what, to think about it to see whether it's in second or whether it's in third, right? So, but they're pretty low, right? So that's why you have a whole bunch of data redundancies, right, in this design, right? So that is how everything fit together. So in the exam, right? So what do we really want you to know after this course, right? So the skill we want you to know, to handle is, given an entity relationship diagram, you should be able to read it and understand what we are trying to do, right? And try to understand that application. And also given one application, right, we might describe it in English, right? You should be able to model it using entity relationship diagram, right? And also given an ER diagram, you should be able to understand, right? So how to translate it into a relational model. And of course, there are so many different ways you can do the translation, right? And we will give you some constraints. For example, we really want you to save space, right? So, and then you think about, what type of relational design can really give me that, right? So we expect you to understand a whole bunch of concepts, right? What is entity? What is entity type? What is a multi-way relationship, right? Primary keys, so on and so forth, right? How to do the translation? What are principles doing the translation between ER and relational model, right? What are the pros and cons of different type of designs, right? So for example, whether to merge a relation or whether not to merge a relation, right? How to deal with generalization, so on and so forth, right? So this is kind of our expectation. And when you talk about exam, right? So you may have a question that look like this, right? That might look a little bit intimidating because it's very complex graph, but just sit down and try to read it, right? So what do we have? We have a whole bunch of entity sites, right? So you have one entity site, which is airport, like airplane type, your airplane, you have flight instance, right? So here you can see, this is a weak relation, it's a weak entity, right? So the seat is a weak entity that depends on flight instance, right? You cannot have a seat without the flight instance, right? So you can have the weak key, right? So, and then you have essentially a flat instance is another weak entity, right? It's kind of like depends on flight, right? There's a whole bunch of relationship between them, just kinetic constraints, so on and so forth, right? So it might look very intimidating, right? But once you know all the concept, you should be able to read it, right? Just be careful, right? So, and because in the exam, like most of the questions are kind of multiple choices, right? So how can we understand whether you like how can we test whether you really understand it, right? So we could have a whole bunch of sentences, and you tell us whether this sentence hold given this ER diagram, right? For example, let's look at one together, right? So there are no two reservations with the same customer name and customer phone numbers, right? So, and how to do it, right? And you look at the reservation, kind of a relation, right? You can see, so this relation has the customer name, has the customer phone, they are the attribute of this relationship, right? So of course, none of them is the key, right? So I could, in principle, put whatever I want in these two attributes, right? So of course, they will not give you this type of constraints, so this is false, right? So this is just kind of one example about our expectation. Given an ER diagram, we really want you to be able to understand the implication of that ER diagram. Okay, so now let's take a break. In 15 minutes, let's get back and we continue to do this type of review. Okay, and in the meantime, if you have any questions, just raise your hand, just speak up. I'll be here to answer your questions. Yeah. Yeah, go ahead.
I just wanted to make another question in regards to freeway relation.
Yeah.
Freeway relations.
Okay.
The example, if you could maybe go back to slide 42, I think was that. So this.
Okay. Yeah, sorry, give me a minute. I wanted to pull out the previous slides. Okay, give me a minute. Yeah, 42 here. Yeah.
I wanted to just quickly ask how, because it's something that always kind of a little bit confuses me in this.
Yeah.
If I give this let's say this works in relation. If I turn the n into a 1, so this one, so I have this
M11.
M11. Okay.
Yeah.
What I wanted to quickly ask was again, how would I read this again?
Okay, so assuming you have this, right? Yes. So the way to read it is to think about it. For every single one, you introduce one functional dependency. So in this case, you introduce two constraints, two functional dependency. Okay.
Okay.
For this one, you introduce one functional dependency in that there's a functional dependency from employee's location to department.
Okay.
If I know the rest, I know this one.
Okay.
Okay. This is one constraint. Another constraint is you read this one. Is if I know the rest, I can decide this guy. That's the functional dependency you introduce.
Okay.
Is that clear?
Okay,
so
that's clear.
Precisely, right? If you have 2, 1 here, you introduce two functional dependency.
Okay. Okay.
Okay. It's clear, right?
Okay, that's clear.
Perfect.
Okay.
Yeah.
Thanks. Thanks. The rest.
Yeah, go ahead. Yeah. Any question, speak up.
I also wanted to ask a question. Is it okay if I just read it out from the chat? Because it was
sure.
Robin asked, will we have some kind of SQL language specification at hand for the exam?
No, at least in previous years, no. We can think about it, but right now I would say no. I think after you read chapter 6 in the book, most of the queries in the exam should be pretty easy to do. Yeah.
Okay, and then I wanted to ask another question.
Yeah.
I was just curious about the exam question for relational model with the airplanes. You show us later.
Yeah.
And then you discussed question 1 with us.
Let me pull that out. So give me a minute. Which one? Oh, this one. Yeah, sorry, just 1 minute. Sorry. Okay, here, right?
know about the relational model with the airplanes. Was the last slide you showed us?
Oh, you mean the ER diagram with airplane?
Ah, yeah.
Okay, sure. Okay, sorry. Yeah, okay, now I understand. Okay, cool.
Entity relationship model. Yeah, I mixed them up. Sorry.
Yeah, go ahead. Yeah.
Yeah, and you discussed with us the first exercise or the first question.
Yeah.
And then I was wondering about the second one.
Okay, let's do that together. Okay.
Where the seat number is a key. Why isn't it unique? And
no two reservations is the same seat number. Oh yeah, and because this is the so if you look at this, right? So this is a weak entity, right?
Yes.
You can have two of the same seat in this with the same seat number in two different flat instances, right? So just like you have a building, you have a room, you can have two rooms with the same ID in different buildings, right?
Okay, I got it. Thanks.
Make sense? Yeah.
Yeah, thanks.
Yeah, so for all this, go back to the previous lecture, go back to the book, right? So once you understand those concepts, it should be easy to do, but you really need to like understand, okay, there's a weak entity, right? So that is like why this happened. Right? Yeah. Yeah, if you have any questions, go ahead.
I have a question.
Yeah.
On slide 28.
20 what? 20 or 20?
8.
Oh, sorry. Yeah. Okay, go ahead.
I don't get why the answer is 0, 3. Like I get the 3,
Yeah.
but I get why the other would be 0.
Why the other would be 0?
Like the second query, I don't know why it returns 0.
Yeah, so you probably give me a minute to read it. Professor. Okay. So the first query is going to give you 3, right?
Yes.
Yeah. So the second query, if you think about it, what would you have? After this where, you will have 3 tuples. You have 1, you have 5, you have 6.
Yeah.
Right? And then you count the age.
Okay.
And then age is all null. Right?
Yeah.
And when you do count x, and when x is not a star, count will ignore the non. So count will ignore the null.
Okay.
Yeah. So I mean that's actually something you need to be really careful about. That is, how does aggregation perform over null values?
So
It's very tricky. Yeah.
But if it were star, it would like have a null, like it would count the null, like as a group.
If it is star, I believe it's going to give you 3.
Yeah. Okay.
Yeah, I mean try it. Yeah, so I may be wrong, but I strongly believe it's going to be 3 if you have star here. Yeah.
Okay, thank you.
Yeah, so like you can try to should give you 3 because star means kind of the whole tuple. Yeah, so they have different semantic. Yeah, but when it's not star, it's going to ignore all the null values. Okay. Yeah, when you have star, it should be 3. Yeah.
Okay, thank you.
Cool.
Sorry.
Go ahead. Hello.
Good day. So with the example before, the question she was asking, sorry, it's early. I basically forgot my question. So if we count over any relation over any, we don't count the tuples that contain the null value. Is that what you're saying?
No. You like for example here when you have count age, right?
Mm-hmm.
You do not count the null values. And for example, if you count surname and age, right? So that's different, right? Yeah. So here, like essentially, like what is aggregation? Right? This is a function take as input a set of values and output one value, right? So that's the semantic of this function.
Sure.
Right. So in that set, we want to count, right? So it's going to ignore all the null values. I mean, at least for this one.
But that was, I mean, maybe I misunderstood Shauna, but when X is star, right?
Yeah.
When X is star, you look at the entire relation and not just the age. And you
That's
said
true.
when counting over star, it would output 3.
3.
But in that case, it would output 6.
Oh no. So here you have where age is null.
Oh, where age is okay. Sorry, I can't.
Oh yeah. Sorry. Yeah. So like I mean for this query, like as a whole, you are going to get 3 out of it.
Yeah. Sorry,
Yeah,
excuse
yeah.
me. Reading is hard. Anyway, thank you.
Cool. Yeah. Okay, so let's sorry. Okay, let's get started. Okay, yeah, so we talked about this, right? So what we are trying to test, right? So essentially, given an ER diagram, we really want you to really understand the implication of that, right? Because that's going to be very useful when you graduate and find a job, right? So when you really use a database system, you communicate with other people about some applications. This is kind of very important skill to have. We really want to make sure you know how to do it, right? Yeah, so there could be similar type of questions, right? So assuming you have an ER diagram, look at this, right? So which of these following statements is true or not, right? So and this is, as long as you understand all those building blocks, right? So in ER diagram, right? And you read this question carefully, right? I mean, you're going to read it carefully and think carefully. It should be relatively trivial to do, okay? So yeah, so we could ask about how to translate an entity relationship diagram into a relational model, right? For example, we give you this very abstract entity relationship diagram, right? So you have entity set A, B, C, D, E, F, G, whatever, right? You have a whole bunch of concepts. You have generalization, right? E is a subtype of A, right? You have a weak entity, right? You have this kind of four-way relationship, right, with different kinetic constraints. Right? Now we can ask, okay, so if you do the translation for entity C, what would be a design that under some assumptions? For example, you remove all the unnecessary entities, and when you talk about generalization, you try to save a storage space, right? Under these assumptions, right, what is a good design for each component, right? So here, I hope it's relatively simple to do, right? Let's say entity C, right? Entity C is a weak entity, right? So I need to have the key from B, I need to have the key of itself, right? You need to have B and C, them together, right? It's a key, right? Of course, I have all the other attributes from C, right? So BCX, BCCX, right? So I'm very easy to do. But then we'll do this for relationship, right? Consider the cardinality, right? So that is actually something very important, right? So like in this case, right, you have this relationship R, right? There is the kinetic constraint that you have one, how to read it, right? So you read that for every single one here that introduce one functional dependency, right? So here essentially it means that there's a functional dependency from AD to B. Right? If I know AD, I know B, right? Which means that AD should be the key of this relation, right? So this is the option B, right? So kind of pretty easy to do, right? So similarly, for example, if you look at this thing, T, right? So this could become a little bit tricky. It's a four-way relationship between E, D, F, G, right? So how can we read it? For every single one, right? So you introduce one functional dependency. So here, essentially, you introduce three functional dependencies. So this one says that there's FD from DFG to E. Okay, if you know DFG, you know E, right? So DFG could be one candidate key, right? So if you know, so like this one means that if you know EGF, you know D, right? It introduces a functional dependency from EGF to D, right? Similarly, like this one introduced DEG to F, right? So you could have three candidate keys, right, for this relationship, right? So in the design, right? So clearly, right, like C is actually a reasonable design, right? I mean, you cannot have B, for example, right? DAF is not a key, right, because of the functional dependency. So, so this is about logical modeling, right? And then we talk about so many different ways for you to essentially enforce data integrity or enforce different properties of your design. The first thing is about constraints, right? And there's a whole bunch of constraints that we talk about. There's a key constraint, a kinetic constraint. There is kind of attribute domains, right? So there's a generalization, right? So there's a referential integrity, right? So how to really enforce it in a real world database systems? And you can do that via integrity constraint, okay? So for example, right, so we talk about the not null constraint, right? So whenever you specify this, it means that whatever value you put into this attribute, it cannot be null, right? And we actually spend a full lecture try to work through different cases, right? Which should be relatively easy to understand. And the primary key, right? You can have this type of constraints, which simply means that attribute or the configuration of attribute need to be unique, and also it cannot be null, right? So, and the tricky thing could be when you actually update the relation, when you change multiple tuples, right? So the result could be non-deterministic, right? So play with this example, right? You will actually see why that is the case. We talk about unique constraint. We talk about check, right? Do local check-in at the tuple level, right? And we talk about referential constraints, right? To specify essentially foreign keys, right? So this one gets a little bit tricky. For example, if you have a foreign key, right, from the kind of lagging in the tens to the lagging students, right? It actually means that whatever tuple you put in the tens table, that student need to exist in the student table, right? You cannot refer to a student that doesn't really exist in the tens table. That is a constraint we want to enforce by using a foreign key constraint, right? So how to define it, right? So we talk about it. And one really tricky thing is the maintenance, right? So for example, if I remove some tuple that has a foreign key constraint, there are so many different things you can do in SQL, right? So if you set the mode to cascade, right, it's going to propagate the update or delete. There's something called restrict and no action, right? So these two can get a little bit tricky, and I promise you guys we are going to talk about it at some point, right? So essentially, if you do restrict, right, it's prevent the deletion of a reference row, right? So if, for example, go back to previous example, you have a tens of students, right? If you try to remove some row in students, right? So if you're kind of the mode, the maintenance mode is restrict, it's going to throw an error, right? No action means that if the reference row still exists when the constraint is checked, you'll have error, right? So difference is that when you do no action, it's going to wait until the end of the transaction, which is, you can think about that as a group of updates, right? It's going to wait until the end to check it, right? And when you have restrict, it will not wait. Okay, so and that's the difference, right? So you can actually read that in this link, right? So, and then you can set default, set null, right? And we talk about different cases. If you do cascade, if you remove kind of one tuple in the student table, right? You are going to also like remove like these two tuples in the tens table because of the foreign key constraint, right? If you do restrict, if you remove one of this, you'll throw an error, right? If you do no action, if you remove this, it's going to check at the end, right? So, and then throw error in this case. If you set null, right? If you remove this, it will set this value to null, right? So on and so forth. So one thing to make sure is you understand that the default mode in database is no action. Okay, if you do nothing, you just specify the foreign key constraint, the maintenance mode, at least in PostgreSQL, the default mode is no action. Okay. So what is our expectation, right? So one thing we really want you to understand after the course is actually how to use it, right? For different type of integrity constraint to enforce in your application, how to write it down, right? So to do that, you need to understand a whole bunch of concepts like not null, unique, primary key, foreign key, and check constraint, right? Understand foreign key constraint of different maintenance mode of foreign key constraint, their behavior, which one is default, so on and so forth, right? So the exam is relatively simple, right? Just to be really careful. For example, we could give you some schema with constraints, right? And you have the book relation with the primary key as a combination of title and author ID. You have another relation called the author, right? You have a whole bunch of like primary key constraint, not null constraint, right? All of this. And then we try to make sure you understand the implication of this, right? So for example, we could have a whole bunch of sentences and you try to tell us whether it's true or false in this relational schema, right? So I mean, this should be relatively easy to do once you understand the semantic of those. So since could like we could also try to go a little bit deeper, right, about the behavior, right, about of kind of query processing when you have entirety constraints, right? For example, we could give you a relational schema look like this. You can see there's a whole bunch of constraint here, right? You can have the primary constraint, not null constraint. You have the foreign key constraint, right? And then we give you, for example, one database instance that look like this. And we say, okay, if you run these two queries, right? So what would happen at the end? Right? How many tuples are you going to have for each relation, right? So here you kind of just kind of like do a thought experiment and try to run it, right? And try to think about, will this one error, right? So will this succeed, right? So what change is it going to do, right? So if I remove the reference tuple in the foreign constraint under the current mode of maintenance, what would happen for that other relation, right? So try to go through that in your mind, right? It should be easy to do once you understand essentially the semantic, right? Yeah, we have one question. Go ahead.
Just a question for this exam question. When the queries are executed, and let's say one of these queries causes an error, would the other queries continue execution? So do we assume that each query runs in its own transaction, or do we assume that they run in such a way that if one of the queries fails, all subsequent queries fail afterwards?
Good question, right? So here here we are assuming you just open PostgreSQL, you do nothing, what would happen, right? So you are actually by default, right? So every single statement will be one transaction. We are going to talk about transaction like later in the course, right? But essentially every single SQL query is its own unit, right? So think about when you do a database, right? So if the first query fail, you are able to run the second one, right? Yeah, so here they are not transactions, right? Yeah, make sense?
Yes, makes sense. Thank you.
Oh, perfect. Yeah. Okay, great. So this is about constraints, right? So, and another thing that we spend a lot of time on actually after Easter is something that we call database design theory, right? So why do we need that? Is as you will see, right? So given one ER diagram, your conceptual model, there are so many different ways you can design a relational schema, right? So from a theoretical perspective, and also from a practical perspective, we really want to understand how to reason about those. What is a good design? What is a bad design, right? So, and that is a question that we are really curious about. We want to formally model and enforce the property that we want in a good design, and we want to reason about it. So one thing that we talk about is about data redundancy. You know, that is really important when you reason about what is a good design, what is a bad design. So why don't we want redundancy, right? Because waste space, right? So it's a kind of, it causes a whole bunch of anomalies. I need to pay additional kind of considerations. You need to be really careful, right? You need to implement different logic, right, to make sure data is consistent, right? So we want to reason about redundancy, right? So the formal way of doing that is to introduce like one way to do it, like to reason about the subset of the redundancy is by define what we call functional dependency, right? So that's closely related to those introduced by cardinality constraints, right? That is, if I know the value of a subset of attributes, I uniquely identify all the other, like some other attributes. So the formulae, right? So if you give me a relation with here 4 attributes, A, B, C, D, right? Functional dependency is between 2 subsets of attributes. Right? For example, you have alpha and beta, 2 subsets, right? So if there's a functional dependency from alpha to beta, right? Usually sometimes you read it, and there's a like for example, beta functionally dependent on alpha, you can read it, right? Sometimes it makes things a little bit easier to say there's FD from alpha to beta, right? In this relation instance, if you give me 2 tuples R and S, right? If they match on alpha, it implies also match on beta, right? So if this is true for all pair R and S in this relation R, we say essentially there's a functional dependency for this instance. Right? If you take this relation instance, right? So we can try to find functional dependency here, right? So you have the FD from A to B, right? Why? Because if I know the value of A, I know the value of B, right? So I have two tuples with the same value A1, but they also map to the same value B1, right? So another example is from this relation, you will not have B to C. Why? Because you have two tuples with the same B2 value and map to different C value. One map to C3, one map to C4, right? So yeah, so that's the definition of functional dependency. Given that, you can actually formally define what we mean by a subset of attribute is a key, right? We first define the notion of super key, right, which is a superset of a key. Means that if alpha is a super key, there is a functional dependency from alpha, that subset of attributes, to all the other attributes in the relation. So, and if we say one set of attributes is a key, right, it needs to be a super key, right? That functional dependency need to exist, and also need to be minimal in the sense that if I remove any other attribute in this set, you will not have this functional dependency anymore. Okay, if that is true, right? So then it means that this functional dependency is minimal, right? And what is a key, right? A key is actually a subset of attributes that minimally decide all the other attributes. We talk about how to reason about functional dependencies. Specifically, if you give me a set of functional dependency that you know going to hold in your application, how can we reason about other functional dependencies that are also going to hold, right? So when we talk about a very beautiful, very simple reasoning system via three very simple axioms called Armstrong axioms, right? So you have the reflexivity, right? That is, if beta is a subset of alpha, right? You will have trivial functional dependency from alpha to beta, right? We talk about augmentation, right? If you have alpha to beta, you will have alpha gamma to beta gamma, right? If we talk about transitivity, if you have alpha to beta to gamma, you have alpha to gamma, right? So what's beautiful about this, we actually spend a lot of time in the lecture to talk about it, is these three axioms together give you a reasoning system that is both sound and complete. It is sound in the sense that if you apply all those axioms again and again, the functional dependency you are going to get is always going to be correct, right? So, and the complete means that all the functional dependencies that hold in your application, right, that is correct, can be derived by applying all those axioms again and again, right? So that is the soundness and the completeness of the reasoning system constructed using these three very simple axioms. So after we talk about this, we also talk about the decomposition of a relation, right? When you have a large relation, usually if you think about why your database design is not good, why there's data redundancy, often it is the case you are mixing so many different entities in the same relation, right? If you have the student attend lecture table, you are mixing two entities. You are mixing students and you are like mixing student attending lecture in that relation. And sometimes we want to decompose that large relation into a smaller one, right? So here we want to reason about the property of decomposition. There are two properties that we care about. One is a decomposition being lossless, right? For example, if you have a large relation, right, you can decompose it into R1, R2, right? Each R1 is just a projection, right? So if you do this type of decomposition, the decomposition is lossless in the sense that if you join R1, R2, you can always get back your original R. It's lossless if one of these is true. Either you have a functional dependency from intersection of R1, R2 to R1, or you have the functional dependency from R1 intersection R2 to R2. Okay, so essentially, when I have the large relation R, I have three subset of attributes, alpha, beta, and gamma. If I do a decomposition to keep alpha and beta in R1, beta and gamma in R2, right? So as long as either I have the FD from beta to gamma, or I have beta to alpha, I have beta to gamma. As long as I have one of these, my decomposition will be lossless in the sense that I join R1, R2 together, I always get back my R. So another property is the decomposition is kind of preserving functional dependencies, right? So what do we mean by that, right? If you decompose R into R1 to Rn, right? So, and you take all the FDs in each of these relations, you put them together, you calculate the closure. If you, that should be equals to the following, that is, you take all the functional dependency in the original relation, you calculate the closure. If these two are the same, it means that we are preserving all the functional dependencies in this decomposition, right? So again, like remember, we cannot specify functional dependencies across relations. So this is one example. You have the zip code, right? So assuming we have like kind of these two functional dependencies, given zip code, you know city and content, given street, city, content, you know zip code. So, and we can decompose this 4 attributes into these 2 smaller relations. One contains zip code and street, another contains zip code, city, and content. Now, multiple questions. First one, is this decomposition lossless? So here I made a mistake in lecture 11. I said no, but actually yes. Thank you. Yeah. So thank you for realize this. I was wrong when I talk about this. So this decomposition is actually lossless. Why? Because if you think about this decomposition, you take the intersection of those attributes. Here is zip code, and you try to see whether there is a functional dependency from zip code to a city and content, right? So in this case, that functional dependency exists, right? So that actually satisfies the condition we set previously when we talk about lossless decomposition, right? So this decomposition is actually lossless. Okay, so I updated this lesson in lecture 11. Sorry about that. So whether this preserve functional dependencies, right? So this case is no, right? Why? Because like there's no way you can recover the functional dependency from street, city, content to zip code, given functional dependencies over this kind of 2 smaller relations, right? So in this case, it actually doesn't preserve the functional dependencies. So what is our expectation? Yeah, so go ahead. I think we have one question. Yeah.
Yeah, to the slide we had.
Yeah.
So there's we have the functional dependency between the zip and the city canton.
Yeah.
Also between zip and street. Like in
okay, so like we have functional dependency from zip city content and the street city content to zip.
No, but I'm saying when we decompose.
Yeah, so when we decompose, right? So in this relation, in the smaller one, like for cities, right? So you have the functional dependency from zip code to city content, right?
Yes, and
for this one, you have nothing, right?
Why don't we have from zip to street?
Oh, because that doesn't exist in your original applications, right?
Okay.
Right, so like given a zip code, I cannot decide street, right? There could be 2 streets with the same zip code.
Okay, yeah.
Yeah. Makes sense?
Yes, thank you.
Okay, cool. Yeah. Also, thank you for realizing like I was wrong. Yeah, so in lecture 11. Okay, perfect. Yeah. So, and what's our expectation, right? So we really want you to understand the notion of functional dependency, because when you build applications, it's so important. I mean, if you do not understand this, highly likely, I mean, you are smart. You can start the reasoning process from scratch and do a good design. I'm confident in that. But knowing the concept of functional dependency will make that process much easier, and you will be more confident in your design, right? So we want you to understand essentially the concept of functional dependency, right? And given an ER diagram, right? Try to write down all the functional dependency you can have, right? Like that can be implied from the ER diagram, right? For example, you have some kinetic constraints. We actually did that practice like in the first half of this lecture, right? So given an ER diagram, given a functional dependent, given kinetic constraint, right? So you can actually derive a whole bunch of functional dependencies that constraint implies, right? So, and also given a set of functional dependencies, how to infer about the new functional dependencies using Armstrong's axiom, right? and given a set of functional dependencies, how to compute its closure, how to compute its basis, right? Given a functional dependency, how to check it, whether it's hold or not, by writing a SQL query, right? So to do this, right, you need to understand really what functional dependency is, right? What's its relationship with kinetic constraints and key constraints, right? So what is the reasoning system you can construct with Armstrong's axiom? So the exam, again, is like, it's very simple, just need to be careful, right? So for example, given this ER diagram, right? So we want to see whether it implies each of these functional dependencies. So let's look at one example together, okay? Let's look at, for example, this one, right? So let's look at this one, B to D, right? Whether this ER diagram implies B to D, right? In this case, you have relationship R2, right? So essentially, there is a many to one kinetic constraint here, which means that if I know B, I know D, right? So there's a FD from B to D, right? That is why you have B to D here. Let's look at another example. For example, you look at R1, right? So this kinetic constraint only tells you two things. You look at this one, you have FD from the rest of entities A to C to B, okay? You look at this one, you have FD from AB to C, and this is all this kinetic constraint going to tell you, okay? Clearly, it doesn't tell you A to B, right? So that's why it's false. It doesn't tell you A to C, that's why it's false, okay? So again, it should be relatively simple to do, right? So here, for example, it tell you AB to C, right? You have AB to C, yeah, I mean, it's tell you that, right? So another thing that's interesting, we actually didn't talk about in the lecture is, if I give you a functional dependency, for example, I have a relation R, and I have FD, BE to D. You can actually check whether it holds or not inside a database, right? So you can do that by writing a SQL query. Essentially, what you want to do, you actually try to say, whether there exists two tuples have the same B and E value corresponding to the same, corresponding to different D values, right? So, and in this case, right? So which SQL query corresponding to that, right? So that is something you might want to think about, right? And but once you go back to the original definition of functional dependency, this one should be pretty natural to do. Okay, once we understand the notion of functional dependency, right? So we can try to reason about different type of data redundancies inside each of these design. And the way we do it is by defining a whole bunch of things that we call normal form, right? We actually did that exercise in the previous two lectures, right? We talk about 5 different normal forms, the first normal form, second, the third, BCNF, and the first normal form, right? So there's a hierarchical structure over them, right? So they actually try to capture different sources of data redundancy, right? So from the first normal form to BCNF, it's try to deal with the data redundancy caused by functional dependency. And for first normal form, as we talk in like this Wednesday, right, it try to capture the data redundancy caused by multi-value dependency. So what's the normal form, right? So database normalization is a process of structuring a relational database in accordance to a series called normal forms, right? So a normal form are just common ways to do normalization. And for each normal form, we actually went through 3 questions. That is, if you give me a schema, you give me a functional dependency, where does FD come from, right? It could come from the ER diagram. It could come from the kinetic constraints, right? Of course, there are other sources of functional dependencies. But given R, given FD, right, how can we check whether it satisfies a given normal form, right? And second, given R and FD, right, that satisfy a given normal form, what are the properties that we can say, right? For example, if it is BCNF, then it doesn't have data redundancy caused by functional dependency. It could have other type of redundancy, but all the FD will not cause data redundancy, right? So, and given a relational schema, given a set of functional dependencies, how to generate a new schema such that it is in certain normal form, right? So actually for each normal form, we talk about these 3 different questions. And we also talk about another type of dependency beyond functional dependency called the multi-value dependency, which actually try to capture this kind of conditional independence between 2 subset of attributes. Right? So here, if the value of B conditioning on A is independent to the value of C, right? So then essentially you have multi-value dependency from A to B, and you have multi-value dependency from A to C. We give the formal definition, right? When you try to think about it, always go back to the definition. It might look very long, but what it's trying to say is very simple, right? So as long as I have T1, T2 here, I must be able to find another 2 tuples that swipe the value, okay? T3, take the blue B and the orange C, and take the orange B and the blue C, okay? So that is what it is try to, like what is very long definition try to tell you. So what is our expectation, right? So we want you to understand the difference between different normal forms. And given a design, we want you to be able to know which normal form it belongs to, right? And also given relational design, right? And if that's not in certain normal form, we want to be able to decompose it or synthesize a new schema that's in a certain normal form, right? We talk about the third normal form, BCNF, and the fourth normal form, right? We want you to understand the notion of multi-value dependency and also how to reason about it. To do this, right, the concept that you need to know is essentially all the normal forms, right? And how to and understand the decomposition algorithm, understand the synthesis algorithm, right? One for third normal form, one for BCNF, and also understand multi-value dependency, right? It's very simple. So the exam again should be simple, right? If you are careful, right? So we could give you a schema, right, with the minimal basis of all the functional dependency you have, and then maybe, oh, give me all the candidate keys, right? So it's easy to do. You just try to find a subset of attributes that minimally decide all the other attributes, right? So from this basis, it's easy to see AC is a candidate key, CG is a candidate key, right? And we could ask, okay, so is this kind of relational design in second normal form? And if it's not, which is the evil functional dependency make that happen, right? So here, if you look at, for example, A to B, right? So your key is AC, right? So your A is actually kind of depends on part of the key, right? Go back to the definition of second normal form. Clearly, because of this functional dependency, this design is actually not in second normal form, right? Similarly, you can do the exercise for G to H, right? G minimally depends on part of the key, right? So because of the functional dependency G to H, this design is actually not in second normal form, right? And you can continue to do this, right? So whether it is in third normal form, like if it's not in third normal form, which functional dependency is the reason, right? Because third normal form is always stronger, right? So of course, like AB, right? So like if AB make this not in second normal form, yeah, AB will make this not in third normal form, right? So you can see AB and GH here, but you have one more evil functional dependency from B to E, right? So go back to the definition, it should be easy to do. And whether it is in BCNF or not, right? So once you understand what each normal form is, this should be relatively easy, right? So, and we could ask you to synthesize a new schema that's in third normal form, for example. We give you a schema, give you a functional dependency, ask you to identify the key, and then try to synthesize a new schema that's in third normal form, right? So this just go through the synthesis algorithm, you should be fine, right? And then decompose it into BCNF. Again, go back to the decomposition algorithm. Yes, it's very easy. And also we may ask you to say, whether this preserve all the dependencies, right? So you can think about it, right? Whether it's really kind of preserve all the dependencies. In principle, third normal form, if you do a synthesis algorithm, it's going to preserve all the dependencies. If you do BCNF, it doesn't have to, right? I mean, maybe it happens to preserve all the dependencies, but it doesn't have to. You would probably need to be careful there, right? So again, right? So for multi-value dependency, it's very similar, right? So we give you one application, and we say, so this is the description of the application, right? So what are the candidate keys, right? And what are the multi-value dependencies that hold in this application, right? And also how to decompose this schema into first normal form, for example, right? So once you understand the property of each normal form, once you understand the definition of each normal form, all this should be pretty easy. So this is just a quick walkthrough of what we have been learning so far, right? So essentially, if you look back in the last, including this one, 14 lectures, we try to teach you to be a good database user. We try to teach you to say, okay, you have an application, how to use a relational database to build that, okay? So in the next lecture, we are going to talk about some advanced functionality in database, which will not be in the exam, right? But is that also very interesting, right? How to do machine learning inside database, how to do data mining database, which is actually my core research field, right? Which is actually very cool, right? So when you go to real world, right? Sometimes you need to do some analytics over your data, and a modern database system will give you such functionality. Okay, we are going to talk about that in the next lecture to make sure you are not surprised when you go to the real world. And then starting next week, we are going to open up the black box of a database system. And we are trying to understand how does that system make it happen, right? So all my data on hard drive, you give me a really high level declarative query language, right? So how can I bridge the gap between this? We are going to go step by step, layer by layer to open up a database system. We are going to talk about recovery. We are going to talk about transactions, right? So all those advanced functionality provided by a database system. It's going to be a lot of fun, okay? So that's all for today. And also for the first segment of this course as a database user. So when you go back home, right? So the best way to learn about the first half of this course is really open up a database, put some data there, run some SQL query, and if the result you get is not consistent with your expectation, give us your question. Okay, we will try our best to answer all of your questions, but you need to be the one to ask it, right? Otherwise, I don't really know how to teach you a programming language. Okay, so that's all for today. And if you have any question, just let me know. We will have another this type of review session at the end of the semester for the second half of the course. And also similar to last year, during the summer, I will have 2 maybe office hours to just answer whatever question you guys have. I think we'll still have that this year. Again, if you have any question, just send me email, post that on Moodle, right? So again, if you have any feedback about how we can run this course better, also let me know, right? We get a lot of feedback and we are trying our best to fix them. Yeah, so that's all for today. So thank you very much. I will see you guys on Wednesday. Yeah. So if you have any question, just speak up.
I don't have a question. I just want to say,
Sure. Yeah.
I probably speak for many of us. Like, I at least really appreciate like this lecture today, where you just tell us like, okay, hey, this is what we expect from you, and this is what we want you to know. This, that. Really appreciate it. It's extremely helpful.
Oh, thank you for the feedback. Yeah, so the reason we are doing this is we are giving you a book with 1,000 pages. It's a little bit hard if you don't give this expectation, right? Yeah.
I mean, fair enough, but like there is a lot of professors who do exactly the same, and well, they don't provide what you just provided in the last hour. So I mean, we don't take it for granted.
No, thank you for your feedback. Yeah. So again, if you have any feedback, how we can help you to learn, yeah, and let me know, right? So I think we are on the same page. We really want to make sure you guys can learn about database, right? So it's cool, right? So whatever we can do to make it easier, let me know. Yeah.
Sure.
Thank you for your feedback.
Sure. Hey, thank you. Anyway, have a nice day.
Yeah, you too. Yeah.
A question.
Yeah,
So,
please.
can one slide back?
Yeah.
Where we have to derive all like candidate keys.
Yeah.
I don't really get how we do that.
Oh, yeah. So that's a good question. Yeah. So indeed, we didn't give you a precise algorithm to do that. So essentially, you check whether you can have, for example, in this case, right, you have A, B, C, D, E, right? So I think the game is to say, so whether I have functional dependency from A, B, C to D and E. If that is true, right, so then it's a candidate key. I mean, and then you check whether it's minimal, right? So,
but how do I construct this dependency from ABC to DE?
Oh, because you have the minimal basis, right?
Yeah.
So these two are all the function dependencies that is true in this application.
Yeah.
And you try to prove from these two whether you have ABC to D, whether you have ABC to E.
With the axioms?
Yeah, with the axioms.
Okay.
Yeah. So like often it is very simple, right? For example, in this case, you have ABC decide D, right? So and then you need something to decide E, right? D also decide E, right? So and then clearly from ABC you can decide E and you can decide D, right? So ABC at least is a super key, and you check whether you can remove A. I cannot. You remove D. I cannot. Remove C. I cannot. So it's a minimal. So ABC can be the key.
Okay.
Right. So like often it's very simple, but there exists a systematic way to do that. You check every single attribute, whether they are key or not. You check a pair, you check a triple, right? You check quadruple, right? So on and so forth.
Okay.
And that is a systematic way for you to do it.
Could you show me how to do with the axioms? Like you did it now very informally. Like how would you do that?
Okay, so yeah, sure, of course. Let me pull out editor. Sorry, give me a minute. I need to share my screen. Okay, so let's try to say we want to. So you can see my screen, right?
Yes.
Perfect. So let's try to see whether we have A, B, C to D. Okay, let's check this. Okay. And your question is how to do that via the axioms, right?
DE.
Oh yeah, for this one it's already there, right?
Yeah, this one is already
yeah,
there.
yeah. Oh, okay. So, sorry, I need to. Oh, sorry. Yeah, okay. So this one's 2D because there, right? So let's do another one. Let's check ABC to E, right? Okay. So let's do this one. So you start, to prove this actually easy, right? So the first step, you have ABC. Yeah, let's abuse it. To D, right? So this is actually given, right, in your minimal basis.
Yeah.
Right. And then you have D to E, which is also given, right?
And then we can just use transitivity.
Exactly. And then you have E because of transitivity. Axioms, right?
But so we don't have to prove A, B, C, D, like comma E. That's like what I thought we had to prove. We just have to prove that.
Oh, okay. Okay. So
both.
yeah, okay. So ABC to D comma E.
Yeah.
This one is equivalent to ABC to D and ABC to E.
Okay.
You prove each one of this, then you get this.
Okay, yeah. Then that
right?
makes it easier because I was confused about that. Yeah.
Yeah. Cool.
Okay, thank you.
Yeah, sure. Okay, so if you have any question, I can answer that like down the road, right? So I have to leave before 10 today. Yeah, thank you very much. I'll see you guys on Wednesday.